So thank you very much for inviting me for this mini course. So I will speak about optimization on random graphs, but for the first lecture I will mainly focus on what are random graphs, what are different models for random graphs. Maybe some of you are all familiar with them, so then maybe this will be a bit boring, but I think definitely not all of you will be familiar with random graphs. So I will just start with the basics and then do some things on random graphs. So why do we have random graphs? Well, random graphs, I think, for at least these days, random graphs are mainly, at least used in inspiration by real networks. So of course, there's many inspirations from networks that we can draw. So you have, for example, social networks. This is an example, a visualization of a Twitter network. But there's also other very interesting networks. So this is, for example, a network of collaborations between scientific authors in physics, I believe. So nodes are here people, and an edge in this case represents if these people two have collaborated. But there's also many other networks. So for example, networks of proteins. So protein-protein interaction networks, these are called. So then all the nodes are proteins, and an edge means that these proteins can together bind and interact. And there's many interesting questions about these networks, but usually, if you are analyzing networks, the problem is that you usually only have one sample data set. So you have one network, so for example, this protein network. Usually these networks are quite large, but still you only have one of them. And for this reason, at some point people started thinking about, can we use maybe random graphs, so random models that create networks of the same size with maybe the same properties, because then if we have these sort of null models, you can also investigate what are the weird properties of this network compared to several randomized versions of it. So there's many ways to do it. So I will just start with the most basic random graph model, which was definitely not invented for this purpose, but was invented in the 60s by Erdős and Rényi. So this is the most basic random graph model there is. So in this random graph model, you have n nodes, and every pair of nodes connects independently with probability p. And so what then happens? So the degree distribution. So for every node, the degree distribution of every node then is of course binomial with n-1 and probability p. Because to each of the n-1 other nodes, you have probability p of connecting. And typically, we are interested in a regime where the average degree, so the expected degree is some fixed constant. So the average degree in this model would be n-1 actually, but let's say n is large, so approximately n times p would be the average degree. So to achieve this, that actually means you have to choose p as a function of n to get a sparse network. And the reason why people are usually interested in these sparse networks is because also in these types of networks, you usually see that the average degree in basically all data sets is usually maybe 5, maybe 10, sometimes a bit larger, sometimes a bit smaller, but even when these networks have millions of nodes, the average degree is usually fixed. So that would mean in this Erdős-Rényi random graph, we choose p equals some constant lambda divided by n. And in that case, you would also achieve that in this model, the average degree is fixed. But that means, so in this Erdős-Rényi random graph, so the degree distribution would be binomial. In fact, if you choose p equal lambda divided by n, you can actually show that it then converges to a Poisson distribution parameter lambda. This is not maybe the most interesting per se, but what is interesting is that if you look at many networks, the degree distribution actually does not look like a binomial at all. So this is just one picture. This is of a citation network. So here on the x-axis are the number of citations that a paper can get. And here on the y-axis there's a frequency. So you see many papers only have 1, 2, 3, 4 citations, but there's also always a few papers with many citations. And in this case, it follows, you could roughly say that it follows a so-called parallel distribution, which means that the probability that the degree of a randomly chosen vertex is larger than y. Let's say we just put equality here, equals some constant times y to the power 1 minus tau. And so in physics, there's many papers that claim that for real networks, this tau parameter should always lie between 2 and 3. So that means, so if you fit this line, which these people did for this network, then you can get some empirical estimate of what this tau should be. Apparently, for real networks, it should be between 2 and 3. But then, of course, this Erdős-Rényi random graph really does not capture this property. So for that reason, people invented several other models which are able to model these networks with these so-called scale-free or power law degree distributions. So one of the most simple models to analyze is that you have, again, n vertices. And then for each of these vertices independently, you draw a weight from this power law distribution. So you give them all a weight, so this vertex is kind of high weight, but some of them will have lower weights. These weights are random and independent, and then given these weights, you connect independently with this connection probability. So the product of the weight divided by n times mu, where mu is the mean of this weight distribution. And of course it's a probability, so if this exceeds 1, you just connect them with probability 1. And you do that independently. And then you will typically see that the vertices with high weight get more connections, because of course this is increasing in the weights. And what you can actually show in this model is that actually the expected degree of vertex I given the weight of vertex I is actually equal to the weight of vertex I. And this is just, so that is just basically just calculating this probability and summing that. But, so the main thing is, so if you use this model, what you can do is you can just, in expectation at least, you can basically generate graphs with all possible degree distributions you like. So here we said, let's do this power law, but actually you can also choose the weights from any other distribution that you like. And then in expectation, you will match the degrees to the weights that you put into this model. So the reason why this model has become so popular is exactly this, so that they call it a random graph model with prescribed average degrees. So if you want, you can tune it to your network data if you have them. And indeed, so the average degree is fixed. You can be a bit more precise. So the degree is actually given a weight. The degree of vertex I is asymptotically Poisson with the weight of the vertex. So we have a prescribed expected degree sequence. But another property of this model is that it's so-called locally tree-like. So what does that mean? It means that if you pick a random vertex and you start doing this so-called breadth first or depth first, you just start exploring your graph. And the children of this vertex, and maybe like this, that means that actually in the first few layers, you're very unlikely, when the network grows large, to encounter any loops. So no triangles, no loops of size 4. So asymptotically, so when the network is very large, this model will be sort of like a tree. There will be some triangles, because of course it may happen that these connect, but this actually happens with a rather small probability. And this actually stems from the fact that that all these connection probabilities are independent. So it's quite, so again, in this model, we have average degree, which is fixed. So in that sense, it should be unlikely that if you choose 3 vertices and you just connect them independently, that they all 3 connect. Because if it would be likely, then it usually would, well, it actually would also imply that your degree would be larger in this sense. Yeah, so this is locally tree-like. And this is actually a property that people usually do not like so much. So, I mean, of course. So, on the one hand, it's a very nice property, because this property actually enables you to prove many things. Because what you can often do is you approximate this random graph model by some branching process, and you can use many tools to prove all kinds of theorems about this model. Not so nice thing is that if you think back about these networks that we thought about in reality, they often do not look like a tree at all. So many of these networks, for example, you can think of social networks. In social networks, if you have 2 friends, it's kind of likely that they also know each other. So it should not be, the social network should definitely not look like a tree. And the same holds, of course, for collaboration networks. So for this reason, many people have started looking into more geometric models. So the most basic geometric model, I think is also probably from the 60s, is the standard disk model. So here again you have n nodes, and let's say that they are on the torus. So here I drew a square, but let's think that this square is actually wrapping around itself and it's a torus. And you put n points in a uniform location on the torus, and then for each point you draw a ball with radius r, and you connect to all the other points that lie within this ball. Now, because of this, you should also get more triangles, because if this node is in a ball of this node, and this node is also in a ball of radius r of this node, it's due to the triangle inequality, these should also be not too far, and it's quite likely that these are also connected. So this model gets many more triangles. Now, I also tried to make this presentation a little bit more interactive. Let's see if it works. Because of the setup, it wasn't possible to do exercises, so I thought maybe we can do a short quiz on this model. So if you have a phone or a laptop, you can participate, but you can also, of course, participate in your mind if you don't like participating on screen. Yeah, that's go back. Well, what is this? Well, let's pretend you did not see the answer. So the question here is: so we have this model which is on the 0, 1 torus. 0. And so we have n uniform points and a radius r around it in which you connect. So how do we choose the radius as a function of n to achieve some target average degree d, which you would like to obtain? And this is in, so here we are in, so this is 0, 1 square. So it's not d-dimensional, it's just 2-dimensional square. So points on a 2-dimensional square uniformly. And then the question is, how can we choose the radius r to get some value of d average degree that we would like to obtain? It also says you cannot vote anymore. I think something is wrong with that. Can I open this? Yes. I opened the vote.
What was the problem again?
So the question is, so we have this geometric graph, we have the 0, 1 square, endpoints chosen uniformly at random, and you connect to everything within radius r. How can we now choose this r so that the average degree for any vertex is d?
And the vertices outside the circle are disconnected.
Yes,
so inside the circle you create a complete graph, right?
Not necessarily, because if this vertex is connected close to this, what? Yeah, within. Yes, within it should be a complete graph. Yes, sorry.
And it's disconnected from the outside, and the degrees outside are 0.
Well, for every vertex you do this, so you may do the same for this one. So for every vertex you connect within a radius r.
Oh, I see. So if your vertices are very further apart, then you may end up with disconnected graph.
It may be disconnected graph, yeah. Or indeed, it may also be a long path of things that are, yes. Well.
But you first create these points randomly, uniformly.
Yes, indeed.
Endpoints.
Yes, so you first, so let's see, so let's just think about what happened. So this is a torus, so, and every point is in a sense the same. So let's say we just put one point on the origin, because the torus is symmetric and the points are uniformly at random. Now the question is, how can we choose the radius so that this point has on average degree d? So this point, so what will be the degree of this node? Well, it will be the number of nodes within this disk. So, the area of this disk would be pi rn squared, and in total this has some area. Well, yeah. So let's say that the area is 1. So the probability, because these points are chosen uniformly, for every point, the probability that lies inside the circle has this probability. Of course, there's also n points, there's actually n minus 1 other points, because one point we fixed, and there's n minus 1 other point. For each of them independently, the probability that they lie within this circle is this probability. So this would be approximately, let's make this an n. So this should be equal to the average degree. And then if you want to make sure that the average degree is, for example, 6 or something, then we just solve this. So then we have that Rn equals the square root of d divided by n. So in this way, in this model, you can choose the average degree. But the not so nice thing is that you can also show that for this model, the degrees are very concentrated. So because every vertex has the same radius, every vertex has the same average degree, but you can also show that it's actually quite unlikely that the degree of a vertex will be much higher than this, because this is just independent random variables, so they concentrate really well. So because of this, people have also made a more realistic model, and I think this is a really nice random graph model, and it's a little bit like the one we had before, but now it's much more realistic because it also includes geometry. So what this model does is, again, it starts with n points. Then we just did as what we had before. Every vertex you assign some weight independently from a parallel distribution. But now we also assume, before that we just drew these points, but actually their position didn't have any meaning. Now let's say that we also give these points a uniform position on some d-dimensional space. Let's say the torus. But it doesn't really matter so much which, but you can also choose RD or quo. And then given the weights and these positions, given them, you draw independent connections with probability, the product of the weights, divided by, again, n times the average weight, just for normalization, and divided by the distance.
So the further they are apart, the less probable are
Yeah.
them to connect.
Indeed, yeah. So there's two ways to get connections. So one, you can be like Taylor Swift, so your weight is super high. Or you're not Taylor Swift, but maybe you live in the same street as your neighbor, and you live very close by. So this is how you can interpret this model. So there's a bit of an interplay. High weights have many connections, and you also see that vertices with high weights connect a bit further. Vertices with low weights typically only connect in close by neighborhoods. And this is actually, so this is a very realistic model, and it has some very nice properties as well. So, for example, so suppose that you condition on the weights of the vertices. So, in that sense, then only the positions are still random. Then the probabilities that I and j connect, they prove that this is so proportional to the minimum of the product of the weight divided by mu and 1. And this is exactly the probability that we had in this non-geometric model. So suppose that you know the weights and you only want to know one connection, it behaves the same as in a non-geometric model. And this property is also not too difficult to prove. So let's say, for simplicity, that we are now on the one-dimensional torus. So that is just a line. And then, what is the probability that I and j connect? Well, so let me go back here, because then you can see what the connection probability was. So, the connection probability was this product of the weights divided by all these things. And now, I want to know what is the probability that I and j connect. So, I can say that I is at the origin.
It's really hard to read now.
Yeah, I don't know how I can turn this on though. Is this better or?
It's better,
yeah, thanks. So let's say that we put vertex I at the origin. And then what is the probability that it connects to vertex j? Well, we don't know the position of j, we do know the weights. So the only thing, so then the probability that I and j connect is just integrating over all the possible positions that j can have. Let's say, so let's take this, so because the torus is symmetric, so the negative part of the torus and the positive part is symmetric. So let's say that we say that j is between 0 and a half. Then we have to multiply by 2 to make sure that we also cover the other half of the torus. And then we just integrate over this. And then, so the distance between I and j, so that would be this term xi minus xj to the power d. Well, d, the dimension is 1. And because xi was at 0, this will just be the absolute value of the position of j. And that is in this case just the variable we're integrating over. If there's any question, also feel free to ask, of course.
Gamma?
Yeah, that's very important. Sorry, gamma. Thanks. And then for simplicity, let's say that let's call this R0. Then here we have to split into cases, because either this thing so if this is already so this one is at its smallest value when x equals 1/2. And if it's already larger than 1 when x is 1/2, then the minimum will always be obtained by 1, no matter what. So there will be no switching point. So if already, if 2 times R0 is already larger than 1, then we will always have 1 in this integral. So then we just get 2 times the integral from 0 to 1/2 of 1, which is just 1. In the other case, then we have a switching point. So we have 2. So when this x is very small, then this thing is large, and we will get the integral of 1. And when x becomes larger, then we have the integral of this quantity. So let's start with the part where x is large. So when x becomes larger than this R0, because when here is R0 divided by x, so when x is equal to this R0, then we exactly have the 1 here. Before that, we then have, and then we get this quantity. So here we have R0 to the power gamma, and then x to the power minus gamma, plus integral of 0 to twice this integral of 1. And then here we can already see, oh wait, here I forgot, this should run to 1/2. Here we can already see why it's important that this gamma should be larger than 1. Because we're integrating over x to the power minus gamma, and usually integrating x to the power minus, well, x to the power minus 1 would give all kinds of extra logarithmic terms, which are not so great. So that is why this extra factor of gamma is actually needed in a connection probability. But you can just compute this, and then you get that this is 2 times R0, 1 plus 1 divided gamma minus 1, plus R0 to the power gamma. So what does that mean? So we get, what we wanted to show was that it would actually be, well, this you could also write as theta of R minimum of R0, 1. And that is actually, so here we have the R0, so when 2 times R0. So when R0 is larger than 1, 2 times R0 is larger than 1, we get a 1. And when it's smaller, we get some constant times R0. So it's not exactly the minimum of R0 and 1, but in order of magnitude, it is actually the same. Here we have a different constant, And the switching point is not exactly at 1, but at another constant, but in order of magnitude, this is the same. So that means that the connection probabilities between individual vertices behave basically as if there's no geometry. Then the question here is, so here, maybe notation here is not so great, but this one you can do again on your phone. So we have that the connection probabilities between two vertices, given the weights, is just basically as if it's non-geometric. Now, suppose that you want to know if a triangle is there. Can I then say that I can say that the probability of some triangle at I, J, K is that equal to theta of min and all the things here. This should be K. WJ, WK. So most people here seem to believe that this is not the case. Does anyone want to say why they believe that this may not be true?
Because of the neighboring property, as you told us, maybe this is the reason why.
So what do you mean there?
If the vertices are very close to each other, then the probability should not behave the same as in independent graphs. Maybe, but that was my intuition behind that, but I may be really wrong.
Yeah, so it has something to do with that. So it has to do with the triangle inequality. So suppose that you have some vertex I, so here what we did is we integrate out over the positions of this j, and then you just say, well, I just look at all possible j and I look at the probability that they're here. Maybe I do that also for some k, but then of course, given the fact that I know that these two are connected, the probability of the distance between these two is not just a uniform distribution anymore, because given that this one is connected to this one, it's kind of likely that these ones are close. Given that this one is connected to this one, it's also kind of likely that these ones are close. So the distribution between the distance of these points is not the same as the distribution as two uniformly chosen points, because you have the extra information that they should be connected. So by the triangle inequality, we already know that the distance between these 2 points cannot exceed something, for example. So that you can do this for individual probabilities, but once you hit a triangle, you cannot just multiply these probabilities anymore. And this is exactly the reason why this model has more triangles than the other model, because here, once you know that these ones are connected and these ones are connected, their distance is likely to be close, and because of that, these ones are also more likely to be connected. Now, one more question. So suppose that I now just want to know what is the probability that I and j and k form a wedge. So a wedge is basically this. So I in the middle, k and j here. And then the question is the probability that I see I yes, I have I in the middle here as well. And then if this is just the multiplication of these two probabilities given the weights. So this is going to be a very close vote. Does anyone care to give a reason for their yes or no? Or maybe it was just random guessing. It's explained almost 50-50.
I think it should be yes because it shouldn't always be no.
It should be yes. Yeah. Good point. Well, yeah, so this reasoning turns out to be correct because in this case, so if you're interested in a wedge, you can of course first, for example, compute the probability that I is connected to J in this just the same way as that we did here. Then you get this Pij. Given that you maybe, given this thing, you have some implicit information about the distance between I and J, because you know that I and J are connected, so you have some implicit information. But the point is, once you then want to know something about the third node, this node still has a uniform distribution on the d-dimensional surface, because the only actually information that you have is this one. So here, once you want to know what the probability that it connects to this one, you don't have any. There's no information about the position here, so this one will just have a uniform distribution on the plane as well. And then because of that, you can then just apply the exact same integral where we actually here we use the uniform distribution. And then you get that this will also again, but then just by J replacing by K here, you get the same thing that it would be minimum of Wi Wk divided by mu n. So this actually holds for all. So you can also make a tree even more involved. But as long as you want to compute the probability that a given tree appears, you actually don't need the geometric information at all. The geometric information only starts to play a role when you want to know something in which some loop appears, because once a loop appears, then, well, this part is still a tree, but then here you have some implicit information about the distance between these two, and then you cannot just use the non-geometric versions anymore. Yes?
All this is after you've conditioned on the weights, right?
Yes, after you, yes, that's a very good point. This is after you've conditioned on the weights, because indeed, if you don't condition on the weight, then of course, if you know that Y and J are connected, that I and J are connected, then you also, of course, it's more likely that I has a higher weight, for example, and then it's also a bit more likely to connect to a third node K, because you have some information about weight. Yeah. Now, so there's one final model that I would like to discuss for today, and this is a model that has had a huge amount of popularity, mainly in physics, which is a hyperbolic random graph, and that says that you should actually make random graphs not in Euclidean space, but in hyperbolic space. So here they say you should, well, you have a disk of radius r, and then you have some points, but now they're not uniformly distributed. They're distributed, well, their angle is uniformly distributed, but the distance to the center follows this specific law. And this basically means that you're very likely to be very close to the border. You're not very likely to be here. That's what you get if you draw this distribution. And then they say they connect nodes at hyperbolic distance. So for every pair of nodes, you connect them when their hyperbolic distance is smaller than r. So it's, in a sense, it's a little bit similar to the simplest geometric random graph model I showed you before, but now we do everything in hyperbolic space. So, for example, for this node, the hyperbolic disk of radius r looks somewhat like this. I think it should also end here, so there may be some small numerical error. But in any case, so this is a hyperbolic disk, so it's not really a disk. And what it also happens is that if you are here, then your hyperbolic disk will be very large. If you're close to the boundary, your hyperbolic disk will be something like this. So this makes sure that you can also see it here, that nodes who are very close to the center, they have many connections because their hyperbolic disks are very large. Nodes that are like here will have only a few connections because their hyperbolic disks are very small.
You have two capital R's. Are these R's?
Yes, these are the same. Yes, these are the same, and that is to ensure that the average. Of course, you could also put some constant in front of this R, but these ones are the same to ensure that the average degree is fixed to some specific function of alpha. Yeah, but they are the same R.
With n tends to infinity, capital R also tends to infinity.
Yes, indeed. Capital R also tends to infinity, but if you choose it in this way, the average degree will still be constant. So if this would not tend to infinity, then the graph would tend to a complete graph. If you let the radius, if you let the space be very small and you just put many points in them, then at some point they will be connected to almost everyone. If you let it go to infinity too fast, of course, then the graph will be empty, and this turns out to be the right scaling. And so here, the hyperbolic distance is defined in some, so the hyperbolic distance is the product of hyperbolic cosine of the two radii minus the hyperbolic sine times the cosine of the angle between vertex I and vertex J. Now, you could wonder why would you actually even want to think about random graphs in hyperbolic space. So I just put a picture here also of a Dutch artist, Mr. Escher, and he actually, he was not a mathematician at all actually, but it seems like he did know hyperbolic space and it made him very popular. So here we also see the same fish appearing everywhere, but here close to the center the fish are much larger because here the distances are actually smaller or larger or whatever. At least things that are in the center have more weight than the things that are here very close to the border. And that was also a sort of an inspiration for this hyperbolic random graph. And since then it has actually also been used very often in practice. So for one of the, I think this paper has over thousands of citations. This was for network epidemiology. So this person proposed that you should use the hyperbolic network to map back all the cities in the world to a hyperbolic graph in some way where he said, well, because you cannot just use the map of the world. Because, for example, if you are close to Berlin, you can reach all other destinations in a very short amount of time. And maybe if you are maybe somewhere in a rural area in let's say Australia, then you may be actually further away from another part in Australia than someone in Berlin is from someone in maybe even in New York. So he made some sort of mapping where he says, well, so this angle here has something to do with the geography. So here I think he also so here it means that you're geographically close, but more to the center means that you can actually also reach many other large cities. Yes?
Do you know which city is in the center?
I don't know.
From which you can reach a destination very
Yeah.
easily.
I think, or maybe this is the simulation where they, because what they actually did is then they said, well, suppose that an epidemic starts spreading at some point, it will not start spreading on the real map, it will start spreading on the hyperbolic map. Because people will travel and it doesn't matter if the distance in kilometers doesn't matter, but the distance in time is actually what matters for an epidemic. Because if you can reach another city within a few hours, you can infect someone within a few hours. If you can reach a city only within 20 days, you cannot infect that person within so much time. So maybe this is the one, I'm not sure, maybe this is the seed node where the epidemic starts. And they show that actually if you look at this for real epidemics, that if you map the distance in the hyperbolic space to the distance, the time at which it would be infected, it seems to work out quite well. So just as in one example, but there's many examples where people use this hyperbolic random graph. Another example is this trade network, which tells you how much trade is there, for example, between China and USA. And there again, they say, well, it says, so here's, I think this is Germany. So here we say, so it has something to do with the location, because here we have all the European countries, here more the Baltic, well, Germany as well is, well, in any case, so here there's more the Asian countries, but then also there's something, if you're more to the center, then you're very important and rich, so you're also more likely to trade with countries that are far away. If you are Belgium or Netherlands, you're more likely to stay close to the other European countries. Anyway, so this is just a reason why many people thought like everything should be hyperbolic. The interesting thing is that if you look at this network more, random graph model more carefully, you can actually, you don't need the hyperbolic geometry at all. So it's very nice for the pictures and to relate it to this hyperbolic geometry in art, but it's not necessary actually. So let's see how this works. I will first release this one. So what we want to show, because before what we had this geometric random inhomogeneous random graph, and we would like to show that this model is actually roughly the same as this geometric inhomogeneous random graph that we saw before. So to do that, we just have to define some things. So we have, because the geometric inhomogeneous random graph was on the 0, 1 torus, this one is on the circle. So let's say that we divide the angles by all by 2 pi, because then we're also between 0 and 1. We're already, so we say this x of u is now not the angle, but just the angle divided by 2 pi. And then we also define these types. I will write them down. These are maybe a bit vague, but they will maybe become clearer in a while. So we set these types as e to the power r, where r is the radius of the disk, minus the radial coordinate of u, divided by 2. Now, what we want to say is, so we want to show something like what we had before. So that given the weights, the connection probability was roughly the product of the weights divided by the mean weights and n. So what we want to show is, so given the types, so or given the distances RU and RV, what, so if we have, so here, maybe here we have a point with RU, and there it has some hyperbolic circle. And then the question is, suppose that this is a circle with radius RB. And then what we would like to say is, so everything with radius RV will connect to the point with radius RU if it's within this hyperbolic disk. And what we would like to answer is, well, how wide is this hyperbolic disk? So what is, in this case, so we want to have, so what is the angle, maximum angle? I should have made this larger. So this is the point with radius RU. So what we want to know is, what is this theta UV? Where here, so we have here, this is the hyperbolic circle centered at a point with radius RU. This is a circle with radius RV. And we want to know, so what is actually the angle between RU that the point with radius RV should have in order to still be able to connect to RV. Is that question clear?
Can you say it again, please?
Yeah, so I have two, so what I want to I want to know when are a point with radius u and radius v connected. Well, they are connected if, so this RU, we can put, let's say, just at this direction. So they are connected if the disk of radius r around this point with radius RU, if it contains this other point. Now we know that the other point is radius RV, so it should lie somewhere on this radius. And then I just want to know, just to quantify what is this one, I want to quantify what is the angle here, because then I know what the width of this segment is, basically. So, and in other words, that means, so when do a point with radius RU and RV, because here, actually this is the point when the distance is exactly r, because this is exactly the point where they hit each other. In here, the distance is strictly smaller than r. So, what do we do? Well, when do points u and v have exactly distance r? Well, this is just the definition of hyperbolic distance. It's not great, but this is what it looks like. But here you can already see that you can simplify quite a bit because r will grow in n. So this thing you can actually ignore. Ru is also actually growing, you could say, you can safely say that this is growing. You can also safely ignore this one, this one, this one, and this one, because they are small compared to the others. So then you're only left with this, which already looks a bit better. Then what we do is we can slightly reorganize this. So this e to the power RU, RV, we take it to the other side. And you can actually write this as e to the power r minus RU minus RV squared. Or if you add this extra term, you can also write it as e to the power 2r minus RU minus RV squared, if you just put this extra thing. So why is this useful? Well, we have this type of u, it's also still there, which is e to the power r minus RU. So this, here we just have the type of u times the type of v. And then here I also use that we had this, that this r was actually also log of n divided by some constant alpha, which controls the average degree. If you write it like that, then we now get this equation. So we get that points u and v are connected if the product of the types divided by n is approximately 1 minus the cosine of the angle between them. Well, we can rewrite this further. You can also, because we wanted to know what is the angle, what can be the angle in which these two are connected, so then we just solve for the angle, and then we can say, well, they're connected if their angle is at most the inverse cosine of this thing, which is actually equal to the inverse sine. So what did we learn? So we have 2 points u and v, we define some types, and now we say that they are connected if the product of their types divided by n is inverse sine, the inverse sine of the product of the weights divided by n. Well, actually, I cheated a little bit. It will be the minimum of the inverse sine of the with 1, because actually in some, well, if at some point the hyperbolic disk contains the whole plane, but you can, that is something else, so so then it is actually also a probability. So then this means that we can actually transform this hyperbolic random graph to something which lies on a 0-1 torus. So we had before that we had the in this hyperbolic random graph we had the positions which are uniform. Well, what we can do, so we had these axioms that were the theta or u divided by 2 pi. These are now actually also on 0, 1 uniformly, because we just make the 0, 2 pi angle, we make that into a 0, 1. And what is actually kind of crucial, which I will not show here, but you can compute, is that these types, they have actually a power law distribution. You can compute that. So you can, and before in the geometric inhomogeneous random graph, we had independent weights with a power law distribution. So you can actually think of these types sort of as being weights. And we don't, so you can say, okay, now we have these types, which are also independent. And so every point has a position on the circle, you give them an independent type, and you connect 2 points. So we say that the angle between them should be smaller than this, but in this transformation, the angle is actually just the distance, because they're here. And you connect them when the distance between points is the inverse sine of tu tv alpha divided by n. So in this previous model, we had the minimum of WU, WV. Yeah, so you actually connect points when the distance between U, V is smaller or equal. And this model is not exactly the same, because in this model you connect when it's smaller or equal than the minimum of the inverse sine of WU, WV by mu n. But actually you can, so if you Taylor expand this for this quantity small, you get the same thing. So actually this one plot will look something, this is the minimum of x and 1, and this inverse sine will look something like this. So this is, so purple is minimum, and this one is the minimum of sine, the minimum. So they are actually quite close. But in any case, I hope that it sort of shows that these models should be roughly equivalent. And this has actually also been proven by the people who introduced this geometric inhomogeneous random graph. They showed that if you fix some alpha of this hyperbolic random graph, and if you fix the radii, which should induce a parallel sequence, so the types should have a parallel distribution, then it actually gives a geometric inhomogeneous random graph with power law exponent to alpha plus 1. So they also conclude, even in their theorem, so for fixed radii inducing parallel weights, hyperbolic random graphs are a special case of geometric inhomogeneous random graph. You can also prove it when you sample them randomly, but they didn't do it in this paper. In any case, the bottom line is that, so these hyperbolic random graphs have been extremely popular, but it turns out you can also analyze these models with much simpler random graphs with geometry on Euclidean space, where we don't have hyperbolic cosines and other things, but we just have the standard distances, but where you basically encode the hyperbolic space by adding a weight to a vertex. So it's a Euclidean process where you add a point mass to each point, and instead of having hyperbolic geometry. And that was it for today.